So I'll be presenting a study from our laboratory. We recently taken up thermoelastic stress analysis, and we've performing the initial studies on this. So we are working on a okay. So we're already working on a mode 2 specimens, but we started out with a CT specimen on mode 1 on an elastic model, so elastic regime, typical specimen according to the ASTM standard. We are using a FLIR SC7500 camera, and the rest is pretty much standard. We're using very high emissivity camera black ink that gives us nearly 0.97 thermoelasticity. And the rest is okay, is history as you know. So you have the calibration from the ASTM standard. You have Williams series for sigma X and sigma Y, and they're using a multi-point over deterministic algorithm implemented in MATLAB to calculate sigma X plus, to use sigma X plus sigma Y, which is from TSA. And if you start out with the usual thermal equation, you arrive at an expression which is very well known. So this is the first stress invariant. And from the Williams series, you can use, you can combine them to find an expression for that invariant. And we're not using the traditional iterative method because Williams equations are actually linear in the stress intensity factor, and so it's basically a linear problem which we solve with a robust single value decomposition. Actually more effectively than you would with any iterative method. Apart from that, you have a typical calibration procedure which will give you the number of pixels for a certain distance that allows you to calculate the stresses. And there you have it, typical results for a crack length of nearly 13 millimeters, and this is what you measure with the traditional measurement of the traveling microscope. So for different sizes of crack propagation, for different crack lengths, you can extract the stress maps directly from the figure. So we also compare that with a simple finite element analysis, which was done with plane stress elements, and we find that at the region of the crack tip, this is an area of 7 by 7 millimeters. Half a millimeter ahead of the crack tip, and these are the results you get for the same cracking limits, and this is actually how they compare. So both the analytical calibration and the finite element method and experimental results. We're not too proud of it. They have this slight variation, and you can look at it here. Oh, okay. Not this one. Oh, this one. But all in all, and given that we've recently only taken out this method, we were pretty much familiar with digital image correlation, but thermoelastic stress analysis is something relatively new for us. So the results we're getting for delta K aren't that different. They compare very fairly to both to the analytical and to the finite element model, and this is what you get for the four track lengths that you saw there. They agree reasonably, not very proudly, yes, but they agree reasonably well. This is just a figure showing the progression of the Y component. So just shows you that the experimental results had a slight variation in Y. So actually, it's not a perfect world. You don't get exact mode one, but yes, it's very similar to that. And finally, this is a comparison between both patterns on TSA and finite element model at one of the track lengths, which with a very small difference. So what we did was obtain the stress intensity factor experimentally with thermoelastic stress analysis through the modified Williams series and using a multi-point deterministic algorithm. And it's okay, an acceptable agreement was obtained between that and the TSA and sorry. Don't know what happened here. Okay. And we're looking at comparing this with mode 2, using the method with mode 2 and comparing what we had done previously with digital image correlation. So thank you. And we have time for any question, although this is very basic work, but please just wait. Okay, if
you can go to some light or
which I'd like to see well, if possible, the comparison between the experimental and the numerical one.
At the table or?
Okay, perfect.
Okay.
And now the distance from the notch tip and the okay. Yes.
Yeah, the correct
The curve
starts
on the right starts.
Yeah, it starts there. Yes. Well, additional information to this would be that we're sorry. The loading is dynamic, of course. We preserve adiabatic conditions by loading at least 4 times above the fatigue frequency, the testing frequency. So we were testing at 10 hertz and acquiring at 40 or 50 hertz, I think. Not entirely sure.
Thank you for the presentation. I have a question for these pictures. It's like, why there is that difference between the shape of the lines of the stresses, or using your experimental value? Because it seems for me that that's show different values than the.
You mean the pictures here or the lines?
The
Well,
pictures
because
seems differently.
yeah, true. Because this is a perfect, well, finite element modeling on a simple component, and you get what you expect in a mode one molding. That's been appearance. And this is experimental stress intensity. This experimental stress ahead of the crack tip a certain distance, and you never get to see with thermoelastic stress analysis. To my knowledge, you don't get to see the traditional shape of a stress field.
Yeah, but why
you don't?
Why is that different?
Because one is calculated, it's theoretical, and the other one is experimental. Or there's an averaging of the effect.
So where is the problem? On the side of the modeling or experiment? Where is the problem? Because there is really a big difference between, if you take the left edge of the gradient is completely different.
You mean this?
Yeah. No, and around in the vertical direction. If you compare the TSA and modeling,
the results are not that different.
I know.
They're reasonably.
I know, but what's your opinion? That is the problem in TSA.
I really cannot answer you that. It's just the TSA will give you a stress map directly, and this is the pattern that you get directly from it. I've never seen TSA give you this before. I can't really answer you.
Yeah.
Why? Please. But I would like to know where.
So heat is generated at the crack tip. Is that also incorporated in the fan so that you get heat dissipation into the sample? So can that explain the difference between the lines?
I'm not entirely sure. I'm not entirely sure if the model, but I don't think the model included it generated at the crack tip. You might be right.
Sorry, maybe this was said before, but what's the spatial resolution of the TSA method? I mean, for 1 point, 1 measurement point, over what surface is it averaging? Do you have an idea?
I don't have the value. It's much more, well, but I think it's compatible with the finite element mesh.
Okay. So same order of magnitude.
Professor Mezos, you ask me?
To use the heating at the crack tip, you will change the stresses at the crack tip, and the stresses at the crack tip are pretty well in both methods nowadays.
Sorry.
In the plot, the peak stresses match pretty well for both methods, for the finite element analysis and for the experimental measurements.
Mm-hmm.
Only the slopes and the shape of the curves are a little bit different. Might be thermal diffusion is different or something like that?
I don't think so. We're following both amplitude and phase. So we know there shouldn't be a thermal diffusion concern here. We don't think we're losing heat fast enough, so we cannot measure. But I couldn't really answer why they're so different. But I don't think it's a thermal diffusion process. On top of it, we were acquiring very fast at 40 hertz or 40 or 50 hertz. So it's over 4 or 5 times faster than the loading. So there shouldn't be an adiabatic concern there. Okay, if there are no further questions, thank you for attending.